Just again. सुनना मैंने आवाज आ रही है. Good morning. Good morning all. I'm Dr. Abhay Dashora. Here we are going to start meeting in just 1 minute. So I'm requesting all the participants to, if you all are ready to start the webinar, please type ready in the chat box, please. Yes, there are so many readies are coming. Okay, everybody is ready. Perfect. Ready. So I'm Dr. Abhay Dashora. Good morning all. Geologists, geoscientists, scholars, and professionals from different parts of the country and the world. I'm Dr. Abhay Dashora on behalf of Geo Junction. Welcome you all. Geo Junction is basically a social media face of the organization named the RICH, the abbreviated as Research, Innovation, Development in Geology and Engineering, which is called RICH. The RICH carry out research work, training programs, field-based workshops, seminars, webinars for professionals, research scholars, students, institutions, and companies, exploration companies and mining companies. You can follow Geo Junction on Instagram, YouTube, Facebook as well, where you can get the updates and knowledge regarding the geology world. Many geologists and geoscientists are already associated and following the Geo Junction there. Here with me, team of Geo Junction, there are so many geoscientists are associated with us. Mr. Santosh Lohar, Dr. Diksha Pandey, and Mr. Shubham is with me here in the meeting. And Mr. Santosh will tell you about our upcoming event, this webinar. Mr. Santosh, please.
Thank you, Abhay. Good morning, everyone. I'm pleased to introduce my teacher, Dr. N K Chauhan, retired professor, Mohanlal Sukharia University, Udaipur. Professor Chauhan is going to deliver a talk in this webinar on structures and control of mineralization. Professor Chauhan is a well-known structural geologist and a field consultant. He has served the University Geology Department for more than 38 years. To his credit, about 60 research papers are published in various journals, international journals, and he has guided many PhD scholars. He has worked with many foreign universities and collaborated research work. He has guided in the field of many research scholars, teachers, government trainees from India and abroad as well. He is also known figure in the mineral and mining industries, geotechnical studies, highways and tunnel constructions, watershed development programs, etc. He is also a resource person and advisor to UPSC, PSC's University in India. Many of his students are working in topmost mining industries, central and state government, universities and in India as well as in abroad. So I now welcome Professor N K Chauhan to continue his talk on structure and control of mineralization for today's webinar.
Good morning, friends. Good morning, friends. I welcome all of you to this webinar on structure and control of mineralization. I am thankful to Dr. Abhay Dashora from Geo Junction, who has given me a platform to be before you and to explain you many mineralization and its control. I am also thankful to Mr. Santosh Lohar for introducing me and giving the details of the work where I am associated. I am also thankful to Mr. Arpit, Mr. Subham Daglia and Dr. Diksha Pandey, who are associated and just giving me, hand to hand to organize this webinar. So, all the participants, I once again welcome you to this seminar on this webinar, that is structure and control of mineralization. As I have been introduced, that I've already worked in the Department of Geology, Mohanlal Sukharia University, Udaipur. There I have served more than 38 years, and I was involved in many types of structural and mineralogical, trainings. My first slide is that whenever there is a structure and control of mineralization is there, why to explore minerals? We know that demand for product made from these minerals only, and it requires the constant discovery of new deposits, especially the case of developing countries like India. If we take an example over here, that India is requiring the copper in million tons, about 0.75 million tons per year, and it will reach to in 2025 about 2.5 million years. So from where to get these minerals and suffice the requirement of the copper? For that, we have to search and begin for the minerals with a mapping on regional scale, topographic map and aerial photographs and satellite imagery, prospecting and exploration by various fields. Nowadays, we know that it is very difficult to find out some new deposits because most of them are at a deeper location and grade of ores are lower. Even when a deposit is found, there is no guarantee that it will be economically significant or it's worth mining. So, I mean to say what mining is that the following points need to be taken into consideration when exploration for particularly mineral is done. That size and quality of the deposit should be enough, the geographical location should be approachable, depth at which it is found should be explorable, and environmental impact, which is the major issue nowadays. Environmental and other related issues are there, and the last thing is about the marketability. And this all depends whether we should go for mining or not. Now, another important thing is that why should we study about the geological structures? As we know that, first of all, what are some of the regions that structural geology is important? Here is a fault surface that is formed in 1992 1992, where you are getting a sort of striation where I am putting my cursor. Note the grooves are showing the sense of motion, and slip accumulated and damage was done. In Kobe, 1995 earthquake occurred along the similar structure, and about 5,000 people were died. Though throughout the world, including India, such high magnitude earthquakes are observed in the recent years also, and particularly in India, where we had so many earthquakes. The Kobe 1995 earthquake occurred along a similar structure, and about 5,000 people were died. And throughout the world, including India, such high magnitude earthquakes are observed in the recent year also. So oil drapes are geological structures. Oil drapes are geological structures, and the geometry of layers and structure control hydrocarbon reservoirs. Structural geologists work for oil companies. We are seeing here, there is an example where we are seeing the anticanal trip, where oil has been trapped in the antiform. In the case of fault trap also, the oil has been trapped all along the fault plane. And we are getting another is unconformity trap, where we are getting oil in the unconformity plane. For exploration part, we know that geological mapping is a very important thing, and it is followed by drilling. Field work is the key to all geological studies, of which mapping is the most vital exercise. There are many types of structures are there. We can classify them into two, that is primary and secondary structures. Primary structures, just we want to check the voice, so I am just coding it. Hello, hello. Hello. So there are different types of structures are there. Primary structures are those which are formed at the time of deposition, and among them the most important is mud cracks, ripple marks, and cross beds. The other type of structure which we are getting in igneous rock, they are volcanic, and we are getting the volcanic layering, and we are getting gneissic layering below. Secondary structures are those which are formed after the rock has been formed, and among them important are craters and unconformities. Craters are the structures which is formed by the impact of terrestrial body on the Earth's surface, and unconformity, as we all are aware, that it is formed as there is a time gap between that. Now, structures are described on three scales. It can be on regional scale, it can be on mesoscopic scale, and it can be on microscopic scale. Primary geological structures, they include the geometric features developed during the formation of a rock, microscopic to mountain scale, formed in sedimentary or igneous rock, or provides clues about the environment of formation. Sedimentary structures include bedding, cross bedding, graded bedding, ripple marks, mud cracks, trace fossils, etc. So these are the bedding stratification, where we can clearly see sediments originally deposited in horizontal orientation. There are the other examples where bedding stratification in Grand Canyon in the first northwest corner photograph, where we can see they are horizontal, and we are getting the bedding plane which is identified on the basis of change in color, differential weathering, grain size changes are there. We can clearly identify the primary depositional surface as 0. Here we are seeing the bedding which has been identified on the basis of grain size and the differential weathering. This is also an example of fixed bedding. The important thing is that oldest layer on the bottom and youngest on the always on the top. How to find out this? For that we require some sedimentary structures. That is a cross bed, originally non-horizontal, and there are some cross beds deposited non-horizontal, and we are getting cross lamination. With the help of cross lamination, we can find out the top and bottom of any bed. The truncated side, which is at the top, This is a truncated side, and we can find out this is the top side, whereas another is bottom side. Another important sedimentary feature we are getting as bedding plane. If more than 1 centimeter thick bed is there, we use to call it as bed, and less than that, we use to call it as lamination. Lamination also identified as the basis of change in color, differential weathering, and differential weathering, and the laminations are over there. This is an example of bedding plane, which is showing vertical bedding. There are bedding plane and load cast structures which help in the identification of bending direction. Here you can see there is a slump structure is there, that is load cast is there. And with the help of this load cast, we can find out top and bottom. Here we are seeing the remnants of the insect burrowing in the sedimentary group of rocks. And with the help of this burrowing, which are burrowing always at the bottom side, and the top side is the photograph. Ripple marks are used as a tool for making younging direction, paleocurrent direction, and the depth of the deposition. That is, wherever these ripple marks have been found, they show that they have been found in the shallow. Bedding and cross stratification with the truncated surfaces used in the identification of younging. The same case as with the arrow, we have shown that is the younging direction. There are some primary sedimentary structures which we include in igneous structures. They are flows, veins, dikes, silts, shield and back margins, magmatic flow pollution, flow top marked by vesicles, stout and batholite, genodate on inclusion, magmatic and segregation. This is a slide which is showing the dike rock is there, which is younger to the rock in which it has been included. There are some silts and there are some dikes and with thermal alteration. This is showing the magmatic flow pollution. And there are some flow top marked by the vesicles with which you can find out the top of and bottom of any volcanic flow. So structures need not only be from sedimentary bedded rocks, it can be from igneous rock forming inclusive structures, or it can be the relation between the two set of beds, which also the type of structure. Angular uniformity. Angular uniformity is an hiatus where one bed is deposited, but later on it has been tilted and erosion has taken place and the younger rocks has been deposited over this one. So there is an angularity between the overlying and underlying bed and identified as angular unconformity. There is a non-conformity where any igneous rock is included inside a sedimentary group of rocks. So tectony is often thought to be a synonym of structure. The term structure provides impression more a geometry or a form, while tectonics is concerned more about the mechanism. So let us see how these structures are formed. As I already explained you that there are some primary structures are there which they form in sedimentary as well as in igneous rock, and there are some structures which form after the formation of a particular rock. That is because of pressure and temperature changes. That is ultimately because of deformation. Some new structures are going to form, and that we define as secondary structures. So in deformation there is a process of formation, and we apply the stress. So the forces acting on a rock body to produce stresses, and because of that there is a strain in a particular rock, that is geometrical changes resulting from these stresses which constitute the strain. Now structural elements. Simply speaking, structure is introduced in rocks by applied forces, and the most important force is the force of gravity. This is the reason why all the structures that develop in rock after their formation are called secondary structures, and those which are developed at the time of deposition or formation are called primary structures. There are three types of stresses or the forces which are acting on the rock mass. The most important is the compression, another is tension, and the third one which we define it as shear. In compression, the layer parallel shortening will be there. Compression from one side. In tension, there will be extension on the other side. In case of shear, there is a shear parallel to the different planes. Now, compressional stresses push material together. Tensional stress pulls metal, rock or dirt layer apart from each other. Shear stress is rotational, the stress is parallel to the effect of material. Now shear stress, as it is given in the diagram, if you take a deck of playing cards and if we apply forces given in the red color marking, then there is a shear strength. There is a layer parallel movement is there because of shear. Now, under what condition do rock exhibit ductile or brittle behavior? Rock undergo ductile deformation. Rock undergo ductile deformation when subjected to high confining pressure and temperature. Thus, brittle structures from near the surface and in the upper crust and ductile structures at a greater depth. In this diagram, when temperature is increased and pressure is increased, it starts in a lower side, it shows the brittle deformation, then semi-ductile, and then it is showing ductile deformation. Behavior of rock and stress and strain. The relationship between stress and strain. Initially, when we go on increasing the stress and strain, respectively, then it is behaving like elastic. Later on, it will start behaving as plastic, and in the last, it will behave as brittle. Now, brittle versus ductile. Generally, rocks respond to stress 1 to 2 weeks. They break or they bend. Brittle deformation, when the rock breaks. Example for brittle deformation include faults, joints. Ductile deformation, when rocks bend or flow. Examples for ductile deformation includes fold, collision, lineation, mylonite, and bodinals. So a fault near the surface becomes mylonite at a greater depth. Sorry. On the left side, you can see a diagram in which it is showing there is a small fault is there. But if we trace it at a greater depth, it will become mylonite or a sort of ductile deformation. So secondary structures which develop after the formation of rock body, the examples are fold, fractures and joints, faults and breccia, collision and delineation, metamorphic fabric like contact metamorphic areoles, and mylonite and SC structures. Now, why study folds? We know that folds are beautiful and fascinating, as and when we go to field. Whenever we look at the fold, we enjoy looking at the fold. Folds can be of mountainous scale, intermediate scale, or even we are looking at microscopic. Now, this is a mountainous scale fold is there. Another mesoscopic scale, these are the examples. You might have seen not many folds in the field. Now, let's have some peep of the anatomy of the fold. A fold consists of hinge part. It consists of axial plane, crest, and the fold axis, trough, and the crest, and the inflection point where both the limbs are joined. So, hinge line, the line joining points of greatest curvature on a folded surface. Axial surface, when many hinge lines from a multiple folded layers connect for the plane. Lines when the fold hinge is inclined to the horizontal. In these two diagrams, where it is shown that this is a horizontal fold, where another one we are getting as plunging fold. Now, whenever folded surface, here yellow color is a folded surface of the primary, we are taking it as S0, and this S0 is folded and it has been symmetrically divided with the help of this green color asphalt plane, that is we used to call axial plane cleavage. The intersection of S0 with asphalt will give rise to a lineation, or at the hinge zone where we are getting maximum curvature point will become the hinge line or fold axis. See here, if we just fold these three layers, then there is maximum curvature line where we are joining. It is forming an antiformal hinge line, and there is a synformal hinge line on the synformal side. So hinge, where we are getting maximum curvature, once you are in the field, at least you can go and rest over it. Now let's talk something about fold mechanism. To understand some basic mechanism that operate during fold formation. The mechanism of folding, there are important thing is that the first type is we used to call flexural folding, where mechanical influence of layering is very strong and folding is done by bending or flexing. In case of passive folding, mechanical influence of layer is very weak, folding without bending and flexing. Now, in case of flexural folding, also we are dividing into two. One is flexural slip folding, where layer parallel soaking by buckling, and by layer parallel slip is there. Generally, we are getting class 1B fold. In case of flexural flow folding, it is achieved by bending and flexing of layer, but without slippage along the layer, and generally we are getting class 1B fold. You can take an example. If you take an ice thin slice between the two big slices, and if you put it in the sunlight and try to bend from side by, what will happen? The ice cream will squeeze towards the inside, and this is a best example of flexible flow coating. In case of passive folding, it is generally we are getting in unconsolidated and soft flow. It is achieved by penetrative exertional cleavage, and generally we are getting class 1C, 2 and 3 fold of Ramsey's classification, and here we are getting hinge thickening and limb attenuation. There are also two types. One is passive slip, another is passive flow. In passive slip, we are getting axial plane is visible in the hand specimen, and when it is not visible in the hand specimen, we used to call it as passive flow. Now, this is a diagrammatic representation of flexural flow, and another is flexural slip. In case of flexural slip, there is a layer parallel slippage is there. In case of flexural flow, there is nothing like that. Layer parallel flow we are not getting. Now, flexural slip flow is an important thing where I want to stress on this one. If you look at this diagram, in this diagram, it's very clear that this A layer and B layer, when they are getting buckled together with the help of flexural slip, we are getting an space in the hinge zone. And this hinge zone where the material is getting the least pressure exerted over this one. So migration of material always takes place towards the hinge zone, and it is generally filled with wood bodies. So spaces in the hinge zone formed by flexural slip is of an importance to locate the mineralization. Now, some folding mechanism. In general, we can divide flexural slip folding, natural surface folding, and shear folding. Three types of folding we can divide. In flexural slip folding, layers slip fast over one another during folding, and we are generally getting parallel and chevron folds, which requires deformation in hinge zone of individual layers. In case of flexural flow folding, the layer flows to maintain the strain compatibility and create similar flow. In case of neutral folding, we can divide the outer arc stretching as well as inner arc stretching, and in between we are getting the neutral surface. So along this neutral surface there is no deformation. In case of outer arc stretching, because of stretching in a profile, it is going to give rise to crevices or the joints which are parallel to the fold hinge or fold axis. In the case of inner arc, there is a shortening and may give rise to low angle faults, which we used to call as stress folding. In case of shear folding, if you take a playing card deck and just paint on the side pie and try to slip one layer over another, then rocks are sheared unevenly like a deck of the cards. Now, if we just look at this diagram, there is a fold is there. Initially, it was a straight line, and when we after folding, it is showing a deformation. If we measure its length with the help of a thread all along the folded layer, and if we stretch it, we can find out the percentage of shortening. Similarly, with the help of fold, the particular layer has been displaced away from each other because of extension. And if you measure in a part the original length of this particular layer and the present length, then we can find out the percentage of extension which is taken place. In nature, we know that at one place, if it is contraction is going on, then on the other side there is extension is taking place. It is a simple law where every action has got its reaction, that at one place there is extension, another place certainly there will be a contraction. Now, if you look at the component rock, when it is getting folded by buckling, we are getting a cleavages which are showing a sort of fanning, and they are converging downward in the case of epiform. In case of synform, they are converging at the top side. Now, these cleavages or the planar anisotropy is developed because of the applied pressure and temperature and because of the formation of the fold. This anisotropy always develop, symmetrical to the folded layer. When they pass from one layer to another, depending upon the competency, and following as what we are seeing in the light wave, when it passes from denser to lighter wave, either it deviates or it becomes rectangular to the surface in which it is entering. So when it reaches to competent rock, the angle of entrance is moved, where in case of incompetent rock is at a low angle. Now, the competency contrast also, very important in this case. The competent rock and incompetent rock, their fold profile will be different whenever there is a deformation is taking place. Here we are seeing alternate incompetent rock and competent rocks are there, which are marked with the ICR, and competent rock, both are there. These are the in case of example is from turbidite. And in turbidite, we are seeing that competent rock, they are showing more class 1B geometry. They are coated and showing a sort of parallel fold, where the incompetent rock is showing class 1C or 3, that is similar fold. See here also an example of competent rock. In competent rock, the fold profile is showing class 1C geometry, whereas the competent rock is showing class 1B geometry. There is a competent rock is showing very clear class 1B geometry, that is parallel fold. The thickness of the fold layer is the same at all the places. Now let's see that how the thickness goes. I mean the folding effect, that is during buckling. There are 3 layers as shown here in the diagram. If you look at this top, it's a thick layer, another thick layer, and there is a thin layer in between. And if we start buckling, the thick layer will become more thicker and the thin layer will start buckling and going to give rise to the symmetrical folds. When onset of the further compression, these symmetrical fold will turn into the asymmetrical fold. They will turn into asymmetrical fold, and these folds on the left limb they will look like Z, on the right limb they will look like S, and at the hinge hole they will look like M and W. See here there is an example. There is a major fold is there. On the left side of this antiform, Z folds are forming, and on the right limb S folds are forming, and the axial planar cleavage to this major fold are similar what we are getting in case of these mesoscopic Z and S folds. Asymmetric small scale folds are the tremendous help in locating antiformal and synformal hinges. We are seeing multiple hinges are there. This is an antiform. On the left side we are getting Z fold, and right side we are getting S fold. In case of plunging synformal cases, we are getting S fold on the left side and Z fold on the right side. Now can you just find out what sort of fold it is? Well, like this particular fold. This particular fold is nothing but it's a Z fold. So Z fold, as I told you, it is always on the left side of the antiform. So the antiform side is somewhere here. We are also getting M and W shaped fold, as I have already explained in case of thin layers. When they are coming, we are getting generally in the hinge zone. Hinge zone, it is associated with M and W shaped asymmetric mesoscopic fold. This is an example where we are getting Z-shaped asymmetrical fold. So certainly we are going to get, the antiform. When we approach up on the right side, somewhere we are going to get the antiformal hinge. S-shaped asymmetric mesoscopic fold, which we are getting on the right side of an antiform. So naturally, when we go up, we are going to get an antiform on the left side. Sorry. Now we are getting generally S-shaped asymmetric mesoscopic fold on the right limb of an antiform. Now, how to reach to the fold hinge? We know that at the fold hinge, generally we are getting M and W folds. So here we are getting M and W separate fold. This violet color is showing the cleavage string. Now here the bedding and cleavage both are right angle. Whenever we are getting bedding and cleavage right angle to each other, it means we are at the hinge zone of the first fold. Here also, if you can see, the S0 is clear with the dark blue line. and the S1 is with the red color line, that is the cleavage. So there is an angle between S0 and S1. Here what we are getting S0 and S1 are right angle. So we are exactly at the hinge zone of a food. This bedding plane we have identified on the basis of change in color, change in mineral composition, as well as with the help of differential matrix. See here it's very clear that we are at the hinge zone of an F1 food. This is in quadrant layer where we are getting F1 food hinge. Here also we can find out that bedding and cleavage both are coming right angle to each other. We are at the hinge. It's also an example of F1 food. This is F1 food in phyllite. So to confirm that whether we are at the hinge zone of F1 food or hinge zone of F2 food, we have to break the sample in the field and to find out, and we have to identify bedding. If bedding is folded over there and there is a color and isotropy which is cutting over to this one, it is we are going to call it as F4. In case of F2 food, these S0 connect to S1 or the earlier cleavage is getting folded, and suddenly we are going to get out of it as granulation cleavage. So this is also the cleavage traces. This is L1 lineation. Now L1 lineation can form by many ways. That is either by the intersection of cleavage with the bedding, that is striking lineation, and we are also getting lineation as the traces of cleavage on the bedding plane. We are also getting the cleavage plane under microscope also, where we are getting planar analysis developed by the parallel alignment of the cleavages, and as well as these cleavages are formed by the flexi. So these flexi are visible over here. That is chloride, biotite. So this is the plane which we used to call as cleavages. Folds are characterized by the presence of cleavage or sensitivity connected by shaping. In this left photograph, we are getting there is a presence of cleavages there, and this black color is also cleavage, but this is showing that we are at the hinge zone. In the case of hinge zone of the second food, generally granulations are developed, and these granulations are nothing but they are the microfoods, and which are formed by the deformation of S1 cleavages, which are at right angle to the S1. This is an example from metavolcanics, where we can identify the F2 food, where earlier cleavage has been granulated, and this particular food is F2 food, and earlier cleavage has been granulated, and planar isotropy is done is visible with the help of S2. Now let's come to the linear part. We have seen about the planar. Lineations are the important structures, elements which is all totally defined by fold axis. Lineation can also be indicator of stretching direction. Use of lineation as indicator of fold axis orientation depends on the relationship observed in the region. Lineation can be of two types. Either they may be penetrative linear fabric or they can be non-penetrative linear fabric. Penetrative linear fabric are the intersection lineations, granulation lineations, middle lineations, and stretching lineations. Secant striations or fault plate, striation on bedding plane caused by fracture slip are non-penetrative, and examples I will give you one by one. There is a different type of lineation are there. These lineations have been formed with the help of orientation of the fibers with their long axis. There are four mullions are there. They are formed by the intersection of bedding and the cleavage. And they are the granulation. They are the hinge portion or the hinge line which are exposed and which is showing you the maximum curvature line fold hinges, and it is forming the lineation. They are the traces of bedding on the cleavage plane. They are the lineation which are formed by the striation, that is movement of the block over one over another. Now there are another type of lineation which are formed, which we used to call it stretching lineation. Elongation of lineation due to stretching in these two diagrams. We are seeing that this is the white color lines that are showing the stretching lineation. Here also the stretching lineation has been formed parallel to the stretching direction. Now in the field, we are getting so many types of lineations, and with the help of lineation also we can find out the deformation or the episode of folding in particular place. As in the first diagram, we are seeing the L1 lineation, This alveolar lineation is nothing but the traces of bedding on cleavage plane. They are very strongly developed and most penetrative, most dominant, and we can call it as L1 delineation. In the second diagram, the same delineation has been deformed by the second fold, and we are getting F2 fold. This is the same L2 delineation what we have shown in the last slide have been getting deformed, and the early cleavages has been deformed by the F3 fold. Here we are getting steeply plunging L3 delineation in mica system. Now, if you talk about planetary structures, we define them by many, that is cleavages, cystosity, and pollution. Let us define it at one, that any planar anisotropy developed in any rock, we call it as cleavage. Now, cleavage is nothing but it is a planar anisotrope developed in any rock. The term cleavage is generally used for those planes which develop in low-grade metamorphic rock. Cystosity, on the other hand, is used where the grade of metamorphism is higher, as in mica schist. The term pollution refers to those which have been bended appearance in the bended gneiss. Now, if you see under microscope, prior to deformation, in case of A, it is showing you the randomly oriented samples are there, and in B, most of them after deformation, these flaky minerals, they are aligning over one another. If you look at the cystosity under microscope, we are getting that these flaky minerals, they are aligned parallel to each other. In a field photograph where we are seeing that X0 to S1 has been folded, and it is giving us the fold profile of F2. Under microscope also we are seeing that S1 cleavage has been granulated by F2 fold, and it's a clear cut S1 and S2 both are right angle to each other. There are some of the examples of shear cleavages or granulation cleavages developed in metavolcanics. Development of shear and granulation cleavage in metavolcanics. Same. Here also we are seeing the development of cleavages. These are the development of interchloride schist. Now let's come to the fault. Fault is an important structure which we have to measure. There are two types I told you. One is ductile, another is brittle. So brittle is the example of fault. We are getting normal fault, reverse fault, and strike slip fault depending upon how this S1, if lambda 1 is vertical and lambda 2, so when lambda 1 and lambda 3 are horizontal, then there is a development of normal faults are there. And when lambda 1 horizontal, lambda 3 vertical, we are getting reverse fault. This is when sigma horizontal and sigma 3 is horizontal, we are getting strike slip fault. This sigma denotes the stresses. So sigma 1 is the maximum stress, sigma 2 is the intermediate stress, and sigma 3 is the least stress direction. See the normal fault. There are faults from Kutch region where we are getting normal faults. Fault plane exhibiting displacement. There are in the field sometimes we are observing escarpment, and these escarpments sometimes form because of the fault also. The most important thing by which we can identify a fault, that is the presence of breccia, mylonite, and SC. These are the C surfaces, that is cleavage surfaces, and there is a flattening surface has been marked by the red color. Now, most important thing which I want to stress in today's lecture is the formation of the boarding. Boarding they generally form by the stretching. There are many types of boardings are there. That is garret shape, convex shape, concave shape, and split shape. It's okay. Now, flattening of strong layers surrounded by weak layers may cause strong layers to lake. So, this is the laking over here in both the sides, and we are getting this formation of the boardings. Boardings can be face proud boarding also. Boarding in the case of calcilicate, because of stretching, of the original layer, the competent layer has given rise to the formation of the puddings. When the extension is more, the puddings will get separate from each other and they will show isolated pudding, which were connected earlier. These are the example of chocolate puddings. Puddings in the 3D that just look like dosa put over one another. Now, puddings and tension gases, they also known as derivatives, they are generally forming their axial plane is generally lying parallel to the F2 fold in the present case. Now, these are the tension gases or derivatives formed due to dilation during folding. Now, tension gases formed due to dilation during folding is example from Java, where we are getting S0 parallel to S1 is there, and it has been intersected by S2 plane that is parallel to the F2 fold. Now, whenever there is a deformation, we are getting interferences there, and dome and basin will develop. And thank you. So, irregular dome and basin will develop, and because of that, we are going to get a closed fold pattern formed by type 1 interference. In type 2 dome and basin mushroom pattern, where the earlier fold axis has been deformed at right angle by the second deformation, and if we just get a section from these two, we are going to see that this is the case of axial trace. Green color is the axial trace of first fold. This red color is the axial trace of second fold, and both are right angle, and it is going to give a crescent shape outcrop. Now see here is the intersection of F1 and F2. Here also we are getting the changes there. This is the F1 and it has been folded all along the F2. This is an example where we are getting dome, crescent and mushroom pattern. If you look here, there is a clear-cut height fold is present. There is a formation of mushroom is there, and this mushroom has been formed by the intersection of F1 and F2 fold. Even full form due to intersection of F2 and F3 fold observed in quartz layer, where we are getting a clear-cut height fold present in quartz layer. Now, third type, we are getting convergent divergent coaxially refolded type fold interference, and we are getting convergent divergent type of outcrop pattern. See here, this is an example where we are getting superposed folding. This is the F2 folding. Here is the F1 folding. This is the F2 folding, and this is the F1 folding. In the low diagram also there is F1 folding, and this is F2 fold. Here also in this diagram, and here it will be more clear in case of folded garnet quartz vein in mica schist. This is the closure which is forming a sort of hook, and this F1 folding is there. Here it is F2 folding. Now, this is also an example of coaxially refolded type fold interference, where we are getting F1 fold. This is the axial trace. Blue color is the axial trace of F1 fold, and red color is the axial trace of F2 fold, and both are right angle to each other, showing coaxial folding. This is an example where we are getting F1 fold, F2 fold in the outcrop pattern. Now, this is a folded body of competent amphibolite in less competent banded biotite niche. The body have been folded. It reflects that body was formed at the time of extension, and now it has come in the field of compression, so the body has been folded. So from extension there was one deformation, compression is the second deformation, so there are clear-cut two phases of deformation are there. Now here we are getting intrafolial fold. The limbs of the fold have been attenuated, strongly thin as a result of layer parallel stretching after layer parallel folding. So wherever the folding development was there at the time of compression, and later on it has come in the field of stretching, and it has given rise to the formation of intrafolial fold. Now let's come to our important chapter, that is beauty and economic significance of geological structures. We'll be taking three examples. One from, this is a geological map all around Udaipur. You can see here this is the place Udaipur. In the eastern side, we'll be taking first example of Budli, Tulsi Devi Sarai, where we are getting pyrophorite deposit. Second, we'll be taking from Jindal Iron Ore area, Tirenga Hill, Purbilwara, that is further in the northeast side. And third, we'll be taking example from Tal deposit of Jalol formation, that is in the west of Udaipur. We are getting near Gogunda and Jalol. And fourth example, we'll be taking southeast of Udaipur, that is Lerjing deposit of Java area. Now, this is a geological map around Gudli village, where we are getting, there is a clear-cut F2 folds are there. These are mesoscopic F2 folds, and the hinge zone of this F2 fold has been filled with pyrophyllite, that is sericite mica. Now, this is a sericite mica, mines is there, where we are getting a section. Sericite mica is nothing but it is pyrophyllite. Pyrophyllite is metamorphosed paleosol is there, which is rich in the alumina. This is another geological map where we are seeing that Bodin style is paleo, that is Bodin style, paleosol, pyrophyllite and sericite mica is there. Now another example from Jindal area, where in the kelp niches, in the kelp seas, we are getting deformed iron bearing bands are there. There are 3 hills are there, that's why we used to call it as Tirenga Hill. This is the compositional banding, what we are seeing in the first row, kelp seas and kelp niches. And we are getting bands of iron-rich layers are there, which is getting folded either S or M shape. And with the help of this S shape, we can find out that hinge of the fold will be somewhere on the left side as shown by the arrow. Here also we are getting S-shaped fold, and the hinge of the fold will be on the left side. Hinge of the fold, as it has been shown by the jet fold, it is somewhere on the right side. So you have to identify whatever fold they are in this circle. So you can see here, the clear S-shaped fold is there. Here is the hinge on of the F2 fold. Now why I am insisting to how to identify whether we are at the hinge on or we are at the hinge on of a particular fold, because hinge on during buckling in flexural slip folding is the loci where we are getting the noble minerals or noble metals which are getting migrated towards the hinge on. And in the ancient mining, what we are seeing over here, people they have mined out the important mineral along with iron at the hinge on. So species in the hinge on formed by the flexural slip. This is an example of hinge on filled with our bodies in the ancient mining that people have taken out the material. Here you can see clear-cut hinge on and filled with the ore bodies. These all are the old workings, ancient mining, and people they are very clever. They knew that where we can get the maximum mineral, maximum mineralization along with some noble metals present in this point. So they are mined out only in the hinge zone of a particular field. Now, old working following F2 fold hinges in Bhutia gold deposit also. Here you see there is a vertical shaft they have built all along the F2 fold axis, and they have taken out the material for extracting gold out of it. Now let's take another example of ultramafic and talc mineralization in the west of Udaipur from Gogunda, from Jalol, and from Rekab area. Now at a one place where a detailed mapping has been done in the northeast of Gogunda at Modi, we are seeing that most of this black color marking is of quartzites, and they are showing beautiful ash folds. Now, how these ash folds they have developed? Let's take an example. Let's take this white or the talc deposits are there. Then during first there was part and given us the formation of pudding, and while compression stage coming into the field of compression, most of these pudding they got folded and they are now visible as folded pudding because of F2 fold. And when we go on compressing, because of this F2 fold, asymmetric fold will develop. One of the limb will become thin, another limb will become thicker one, and it may give rise to a sort of asymmetric fold. This position of this ore bodies is because of F2 fold. Now see here this diagram, a clear-cut, separated, isolated puddings are available to us. Now, and they are separated because of F2 fold, and we are on the left limb of a major fold. So if you want to reach to the major mineralization, you have to go straight, then turn to right, and then go straight will reach to the hinge zone. So let's imagine a underground mine, and let's imagine this particular pudding as say 100 meters and having width of say about 5 to 10 meters. And suppose this is mineralized, and we are going to mine it underground. Once we exhaust this particular mineralization, to search out another underground, we need to drill on either side and we'll say there is no continuity. But if you are aware, if we can use this mesoscopic Z as M and W folds, we can say that we have to mine it out, then we have to take right turn because it is a Z fold and we are going to touch another mineralization, then go straight and then touch all right, and ultimately we'll reach to the hinge zone where we'll be getting maximum mineralization. See this example, we are getting that is isolated borings because of, as folding. This was the all continuous prior to this deformation, and later on because of compression, onset of this F2 folding, and because of tightening, because of F2 folding, most of these borings they become isolated. See here, there is an example where people they have mined out the tal in the Gogunda area, and if you see this inside picture, the small picture which I have added over here, you can see the isolated borings. These isolated borings are nothing but here in the field is the tal which people they have mined out. So one pit you can imagine here, and these two imagine pit on the other side. So to mine it out, they have to go to straight, they have to take turn left, and then another. Then they go straight, and then they will, on the left side there will be another. So use of these isolated borings or S and Z shaped fold, one can reach to the maximum mineralization. So this is what I have shown you earlier. That is all controlled by S fold. See here, this major mine is also controlled by S fold. Let's take the last example, geological, that is from Java. This is the map after Stepjet and Srikantan, where we are getting, Zavarmala. This is your Mochia, on the other side there is Bandaria, Goa, and other thing. At Zavarmala also we are getting beautiful sedimentary structure with the help of load cast. We can find out top and bottom. With the help of graded bedding in Gravak and other also, we can find out any direction. Now the first deformation was very intense at Zawar, which is causing transposition of bedding parallel to the schistosity, and effectively therefore S1 schistosity represents the firm surface of the Zawar region. Wherever we go, we will get always S0 parallel to S1. Now, they have been granulation cleavage is the most common feature at the Java because successive folding of S1 has given rise to the formation of space cleavage, and which has been identified as granulations. So, most of the lead zinc mineralization is confined to the dolomite and its variant at Java area. However, economically significant sulfide mineralization occur in dolomite and some of its variant also. The surface indication of mineralization includes the presence of numerous old workings all throughout Java region, or not at Java even, but at many other metallic mineralization, whether it is Kurbanela or the Java mines, or it is other places at, gold deposit at Bukhi also, we have got numerous old workings. So the presence of oxidation zone and limonite weakly developed Gosan zone, particularly in Java area. And there is a large heap of clay along the TD River Valley in Zawarmal area, which indicate a large-scale smelting activity in the past at these places, as has been recorded in the ancient time also. People were mining it, and they were taking out some zinc and lead out of it, and they were exporting at about 2,000 to 3,000 years back also. So in general, the Java road body consists of fracture-filled lobes, stringers and veins with some dissemination, arranged in anaclone lenticular bodies, which make an acute angle with the bedding both in plan and in section. There is a detailed mapping of eastern part of Mocha Hill indicate that longer axis of the old working makes an angle with the primary layering, which I will show you in the next map. The depth-wise extension appears to be parallel to the plunge of the F2 in measuring area. In plan, some of the old workings are virtually demarcated zone of extension that are geometrically related to the extension accompanying dextral shears. Now look, if you look at this particular map, this is the detailed map. Here on the East Motia Hill, where we are getting, this is the bearing plane direction, that is the carbonate rock, which is hosting the main lead zinc mineralization. Now this red color line is showing parallel to the mineralization, which are at an angle to the bearing plane. It's very clear from the diagram. In dolomite, what we are getting, this blue color line is parallel to the bearing plane, and this red color line showing parallel to the shears. So most of the mineralization, they are occurring straight bound, but they are at angle to the bedding plane. See here in this old working also, this is the direction of mineralization and this is the direction of our bedding plane. Here also this is the bedding plane, this is the direction of old working which have been seen. People have mined out all these directions or the ore shoots which are at an angle to the bedding plane. See, at F2 fold, also in the field, when there is a old mining, people they have mined out the hinge region, wherever they were getting hinge zone filled with ore bodies, and where we are getting these tension gases. So examples are known where useful elements and minerals depositing forming in minor quantities, which have been concentrated during subsequent tectonic processes. That is, the impact of first deformation and second deformation, they have migrated, I mean they have concentrated during subsequent deformation these minerals, whether it is in the hinge zone or it is in the limbs. Most preferred depositional sites are axial planes of the fold. See, concentration of useful metals at places occur along the zone of forming ore shoots, which are pipe-like bodies, concentrated bodies, and they are almost parallel to the two-fold, what I have shown in the ancient ore workings. Tectonism played a very important role in the development of such structural sites where ore bodies are concentrated. If you look at the plan, these red color are showing the ore shoots or the ore body, which are at an angle to the bedding plane, and this most of this mineralization is bounded by the bedding plane only, strata bound rather. This is another example in a vertical section also, they are showing some angle to the bedding plane. Here also, if you look at Valeria, look at the Mochia section. So Java ore bodies are strata bound type because of bearing a very few, they are confined within the single stratigraphic unit, more particularly in the pure dolomite. However, except in the case of Jarmala, the ore veins are discordant to the bedding, but most of these ore shoots, they are controlled by the deformation. That is, the steep dipping ore lenses discordant to the bedding planes are parallel to the foliation, which is axial planar to F2 fold, which it is a structural control all along the planar anisotropy developed because of F2 fold. Strict concordance between the plunge of the ore shoot and the F2 fold axis lineation. This could be verified in most cases by the orientation of innumerable old workings which I have shown to you. Now, if you look at the schematic diagram, this S0 to S1 is folded, intersected by S2. So this is the hinge zone where ore minerals occur in exchanges separated by gangue mineral, intersection of S1 and S0 to S1. So this is the F2 fold axis, which is forming the ore shoots, and this is the hinge zone of F2 fold. So let's come to the conclusion. The final interpretation is important to understand the structural control of mineralization. I've tried to show you so many younging data with which you can find out the top and bottom, and you can reach to the relative stratigraphic position of litho units so that you can erect in stratigraphy. The detailed geological mapping with the help of small scale structure using mesoscopic structure like S, Z, M, and W, and using them for the outcrop pattern in the map along with the structural data to reach up to the fold hinges which has developed because of natural folding, and they are the loci of main mineralization for any metal or non-metallic things which I have shown in my most of the slides. That is from the hill hinge, from the fold hinges. People in the ancient time also they have mined out many noble metals as well as lead and zinc and iron and many things, and to map the discontinuous outcrop of the mineralization for exploration and mining. Determination of fold generation we have also tried with the help of folding of lineation, folding of planar features, and based on that interpretation of small structure I have tried to explain. Orientation of large scale fold in smaller domains of cylindrical fold axis can be done with the help of your data and further structural analysis of the region. Elucidation of large scale structural geometry and structural control of mineralization can be understood if we correlate the small scale structure to the regional scale and to the sections and the vertical as well as longitudinal section, and if we can correlate, we can find out the structural control of any mineralization. And with the help of this, which may lead to some new discovery of mineralization. So this was the talk where I have tried to explain you right from the beginning why to study structure, how these structures are identified, how this mechanism of deformation is important for a particular mineral to migrate from one place to another, and the loci where we should go and try to find out the mineral, that is control of mineralization. And with the help of these examples, I have tried my best to explain. Thank you very much. And here I'm ending my lecture on structure and control of mineralization. Thank you.
Thank you very much, sir. So after this presentation, we will start a Q&A sessions, which all the participants has put questions in the chat box. So we will take one by one and try to take as much as we can take in the current session. We need to close up our session at 12:30. So we will start it soon. So if you have any questions, if you have not typed in the chat box, then please put into the chat box so that we can take your questions to answer. Abhay, if you have any questions from YouTube, so please take it up.
Okay, so it was nice presentation by Professor Chauhan, and I hope you all enjoyed it very well. I'm Dr. Abhay Dashora again here, and if you like this presentation, I ask you to write fold in the chat box. Fold is the most fascinating structure in structural geology. And please write your question in the chat box as well. There are so many questions are coming. People are throwing questions towards the Chauhan Sab and Chauhan Sab. This is the unique ask all the questions with them. Questions with me. Yeah, it was the problem on the connection. Yes. If you find the mineral, do some detailed structural mapping, and I hope this presentation is very useful for you. Am I audible? If I am not audible, please write in the chat box. Yes, there are so many questions are coming from. One is from Nagesh Rajpurohit, Dinesh Gupta, Mr. Pakshal Mehta, and a lot of many geologists and geoscientists are trying to do presentation. So I'm asking if John Sab is available. Mr. Santosh. I think it was a long presentation. We just need a break to get water. And meanwhile,
can you repeat the question?
Excuse me.
Hello, Abhay. Are you getting my voice?
Hello, Abhay?
Yes, yes. You
Yes.
are audible.
Okay, thanks. Can you repeat the question? Actually, there was some technical issue from our side.
It's pretty. She's asking how are load cast formed?
Hello. Hello.
Yes, sir. Yes.
Voice, Abhay. Abhay.
Yes, cast are formed.
The question is how load casts are formed.
Yes.
So the answer to this one is the load cast is formed because of the thixotropic condition at the time of deposition. Different layers have got different viscosity. The viscosity, more viscosity material will try to put down the pressure, and because of that, load structures are formed.
Okay, great. Thank you. Thank you very much, sir. Another question is from Samita Biswal. She is asking, fold is formed at the great depth. Then how we can able to see the folds at the surface?
Now, Samita, many rocks are formed at a depth also. Even magma is forming at a very great depth, but due to the tectonic activity, everything is coming up. So we are able to see the folds and everything at the top also. Samita, I think I'm clear.
Yeah. Oh, this is,
Coming to the next question by Shilpi Sardar. How mineralization is controlled by various structures in the field. This I have already shown you in the slide. I have shown you about the non-metallic as well as the metallic mineralization. They are associated with the deformation, and mostly in the case of hinge-on, we are getting mineralization. I have shown about the talc as well as for other minerals also.
perfect, sir. Sir, there is one more question from Mr. Narendra Joshi. He's asking how minor faults are helpful in the major structure deformation. It is a very nice question.
Oh, how minor structure features help in the study and identification of major structure feature. This you can go through a very simple book. These minor structure are the replica of the major structures. I have shown in one of the diagram, mesoscopic structures can lead to the major structure in the field. So if you go through any book, you'll find out the relation between mesoscopic and these major folds. I think Naren Joshi, I'm clear to you. Any other question?
Mr. Dinesh Gupta is asking if you have any good correlation about this new discovery. If you find any discovery because by the use of structured mineralization, if you have any example, it will be helpful for him.
Yes, yes. With the help of this, the new discoveries in the sense that we have tried to apply it on the non-metallics in the Jharwal belt, where actually you can apply these your study only when you have got a detailed map of a particular region, and where you can have as Z and different features on the map pattern. And with the help of that, I've tried to apply in the non-metallic in the talc mineralization in Sarada, talc mineralization in the Jharwal region, talc mineralization in the Gogunda, where it is finally coming applicable. With the help of this, you can reach to the new findings of this mineral deposit without further exploration.
Exactly. Even I can put one example. That is my PhD research area as well, where the copper mineralization is completely structurally controlled, and that is IOCG type of deposit. And For your all information, this my PhD was under the Professor Chauhan only, and he taught me very well that how the mineralizations are controlled. So there is another question about someone is Mr. Prakshal Mehta. He's asking about structural aspects of Agucha ledging deposit.
Rampura Agucha.
Yes, sir.
Rampura Agucha I had been many a times, but I couldn't get any deformation. It is totally shear control. So, I mean, we have to find out the shear indicators, and we have to apply that, and then only we can find out the control. Though it is indirectly, if shear is there, it is a structurally control. I think I am clear to you. We are not getting any sort of ductile deformation over there.
Exactly, there are a lot of possibility to find more Agucha type of deposit by using the structural geology there. Yes, it will be very helpful.
So there is Abhay, excuse me, there is another question from Naren Joshi.
Yes.
He is asking near Debari in Udaipur, Debari formation is there. In Debari conglomerate, thick horizons of stress pebbles are observed. What they indicate? These pebbles are showing you a very unstable environment. You know that conglomerate forms in a very unstable environment, and from the source area it get deposited over there. So when they come under when the stress is applied to this one, they become stressed one. That is strain. We can find out with the help of these stressed pebbles. So they indicate a sort of shearing, stretching, and mostly this we are getting down declination of these pebbles. So they are showing the stretching is parallel to the Archean proterozoic boundary. There is another question: how to differentiate the cleavage plane, fracture plane, and foliation plane in the field by Narasimha Rao. Yeah, Mr. Rao, as I already told, these are some of the confusing terms which I want to avoid. There is nothing like cleavage, fracture planes, or foliation plane. We should use only one term, that is cleavage plane, along which you can cleave a rock and which forms with the help of planar anisotropy. Okay, Subarao, that's a nice question. By how to differentiate between parallel fold and similar fold in the field. So you just go through the basics. Parallel folds, the thickness of the folded layer will remain same either at the limb or at the hinge. But in case of similar fold, the thickness will vary. On the limb, it will be very thin, and at the hinge zone, it will be very thick. I think I'm clear to you, Mr. Rao.
Sir, Mr. Vikas Soni want to know some details about AF1 and AF2 fold.
What sort of detail? How to identify it?
Yes, exactly.
So, yes, you can identify AF1 fold and AF2 fold in case of metasedimentary rocks. So, where you can identify the bedding plane, you have to you must know how to identify bedding plane. 99% they are getting confused with the bedding plane. Bedding plane is a primary depositional surface which can be identified with the help of change in color, change in grain size, change in mineralogy, and differential weathering are there. And with the help of many sedimentary structures, you can find out bedding plane. If this particular layer is getting folded and we are getting cleavage and bedding right angle to each other, then it is F1 fold. Another, if the cystosity which has developed prior to this F1 fold, if it gets folded, then we have to call it as F2 fold. So there is a clear-cut identity is there. Mostly in Aravallis, what we are getting, F1 folds are tight folds, isoclinal folds, they are high amplitude folds, their amplitude is too much, and in case of F2 folds, they are open upright folds, where mostly we are getting granulations, we are getting, buddings in the hinge zone. So once you are in the field, you have to learn from the field and you have to apply there. So nature gives you the clues, and those clues you have to apply back to understand the nature. So I think I'm clear.
Perfectly clear, sir. No one can explain better than you all this AF1, AF2, sir.
No, nothing like that. Thank you, Abhay. There is another question by Nitin Joshi. Sir, how gneiss structures can be distinguished from cyst structure? So this is, what I mean to say is that if you go to the higher grade site, gneissosity means a clear-cut separation of the mafic and felsic minerals are there, and you'll get this felsic or quartzo-feldspathing material all around surrounded by mafic material. It will show you the gneiss structure. In case of schist, I mean in case of schistosity, as we are getting, there is a classification of closely spaced cleavages and then widely spaced cleavages. So the starting from slaty cleavage, as given in many books, from slaty cleavage it starts and it goes to the formation of cleavages in case of schist, where the minerals are identified with naked eye. So there the cleavage present in schist is of a lower grade, in gneiss it is of a higher grade. But planar isotropy will be present in both. One will people used to call it as schistosity, another used to call it as gneissosity. Clear-cut banding is there.
Thank you very much, sir, for the excellent explanation. I think we will request you soon for another presentation on the basic structure as well. So,
Yeah, there are more questions coming over here, Abhay.
yes, sir.
There is a question by Jamna Biswa. Sir, can quartz vein indicate mineralization? If yes, then how? Listen, quartz, one should be not get confused. Quartz is not coming from anywhere else and getting intruded in the rock. It is because of metamorphism of a particular rock. Quartz is a product, byproduct. I'd say it comes out as a silica, excess silica during metamorphism, and during deformation, it occupies the places of where it is getting least pressure. So quartz is not like indication of mineralization, but it is an indication of metamorphism.
Sir, there is one more question from Dr. Ramakrishna Desai from Hyderabad. He is asking, is the structure geology can be used in hydrological exploration as well?
Of course. Why not? In hydrological study, we are applying in Rajasthan. You know that in Rajasthan, or particularly in the southern Rajasthan, we have got a gneissic rock. We are not getting any sort of primary aquifers. They are secondary aquifers. And secondary aquifers are those, they are formed by these fractures and other thing. We don't get to locate these fractures and other thing in a rock. We have to use structural geology of a particular region. If you know the hinge of a fold or the intersection of two planes, so the maximum intersection place is going to give us the good water. I think I'm clear to you.
Yes, sir. It's a perfect explanation given by you. There is another question. Is the joint plane useful in the mineralization or exploration?
No, joint plane can be used because it is a type of structure which always form as a failure. As I told you, whenever there is extension, there is a formation of joints will be there. Now, varieties of joints they form. Suppose if I fold, some joints will develop at right angle to the fold axis. They are at right angle to the fold axis. That is, we can find out the stress direction. Once we are clear about the stress direction, then the strain effect of a particular region is we can find out, and that is the direction along which you are going to get the good mineralization. I think I'm clear.
Perfectly clear, sir. There is one question from Mr. Ronald Jain. Interesting question, sir. Is the brachia useful in the mineralization?
Is there?
Brachia.
Yeah.
Useful in mineralization?
No, brachia as it is not utilization, but whenever there is a brachation of any mineralization is there, then the host rock is going to get reduced. We'll take an example from RSMM Jamakotra, where brachiated ore is high grade. Mostly getting P2O5 is too much in that one, going up to 45%. Whereas in a normal rock, we are getting about 15 to 20%. If brachiation increases or the grade is increases because of brachiation. That is why we are getting in a shear plane or in the shear zone maximum mineralization.
Right. Excellent. Another question, sir. So many people are eager to know and their queries. So another question from Krishna, and the question is how the structural geology can be added to remote sensing and geophysical survey for high mineral potential area or targeting.
That can be joined because listen, remote sensing, you are seeing everything on the map and everything taken from the satellite. And the real basic structural geology is done in the field. Until unless you correlate anything which you are seeing as a remote sensing, you have to correlate in the field, and then you can apply. You can link both together, that is structural geology and remote sensing for any search of mineralization.
Sir, there is one testimonial from Mr. Aino. He said, I love the explanation of F1 and F2 faults by Professor Chauhan.
Pardon? I couldn't listen.
Sir, there is one testimonial. He's saying that I love the explanation of F1 and F2 faults by Professor Chauhan.
Oh, thank you. Thank you.
He's from Africa. And, sir, there is one more question. Sir, I would be great by Ms. Kavita Bharadwaj. She's asking, sir, I would be great if you throw some light about the Kayad lead zinc mineralization in north of Rajasthan and its structural control.
Any other question, Abhay?
Yes, sir. There is question from Kavita Bharadwaj. She's asking, can you throw some light about the mineralization, lead zinc mineralization in North Rajasthan, nearby Kayad area?
Now listen, I have not done any work over there, but once if I get a chance, I'll be able to, if I look at some map pattern or something, I can give her better ideas. At present, I don't have any data regarding that.
Yes, sir. Sir, there is a question from Mr. Vivek Lal. He's asking, purely sedimentary country of Triassic age, I have base metal mineralization. My question is whether the base metal mineralization is the result of structure there as well or not.
It's a because of?
Because result of structure, it means is there also it is structurally controlled? Is there any possibility in the Triassic sediments as well?
Yeah, of course it can be. Why not? We are getting, I mean, some sort of deformation. Once it has started, once in Jurassic, most of the deformation have been done, and many of the mineralization you can age to be something related to Jurassic age.
Miss Pooja Sharma is asking.
Jurassic is much before that.
Miss Pooja Sharma is asking about the metal mineralization in South Rajasthan, in Lower Arauli. In Lower Arauli, at Archean protected boundary, she is asking actually.
No, this metal mineralization I've already explained about the Java.
Yes.
That is in Aravallis.
Yes, and in my PhD area as well, sir. It is totally controlled.
Yes. So, yeah, that we have also located.
Yes. And there is another question. Mr. This ripple marks, about the ripple marks, there is question. The ripple marks plays any role in formation of old deposits?
No, ripple marks I didn't mention about any deposit. That's a purely sedimentary. With the help of ripple marks, we can find out top and bottom, and sometimes we find out the paleocurrent channels. As we know, if you know the paleocurrent channels, there are some detrital zircon and detrital many metallic minerals. They may come and get deposited in a particular sediment. So with the help of these ripple marks, you can find out the flow direction. You can find out the depth of formation of that particular rock. And it has ripple mark doesn't give directly indication of any mineralization. Thank you.
Excellent. And there is one more testimonial for you, sir. Mr. Rajendra. He said he always see the two topics. One is structure and one is mineralization. First time he saw the any presentation which is correlating both of them and the pure applied aspect of structural geology.
Thank you, Abhay. This was actually my aim right from the beginning. Whatever we are learning in the field, these small scale structures, if we cannot apply any structure or the study what you are performing in the field, in case of for searching any mineralization, then I think it's not true efforts towards the subject. So these small scale structures can lead to some new mineralization. As in my last conclusion part, some of my students are working all along the Archean proteogenetic contact, right from southeast of Udaipur and just going further in the northeast of Udaipur. And in future, what I am planning, this small scale structure to the map scale, if we join together, no doubt, this nature cannot be, biased to give only a few mineralization. If there are must be so many are there, just looking to the Rampur Agucha, a very big deposit cannot be isolated. There must be some more, but we should know and we should try to find out the way by which you can such thing. And I hope in the future we'll have similar some new deposit also. Thank you.
It's great.
Okay. Abhay, do you have any more questions there?
Sir? Sir, can you hear me?
Yeah.
Yes, sir. Sir, another question is by Mr. Sanjay Minda. He's asking spacing of joint with relation to deformation. Please explain. The relation between the joint plane and the deformation.
Okay, this I have already explained to one of the participant that joints they do develop in a many ways. They can be budding joints can be there. There can be diagonal joints can be there. The joints parallel to axial plane also can be there. So the spacing between them, we used to call them by many workers. They used to call it as joint plane, fracture plane, and other thing also. So this joint plane is not at all related to any mineralization, but it gives us the clues about the deformation or an identification of particular deformation.
Thank you, sir. Thank you very much. There is one more testimonial for you, sir. This is from Ramnandar Kumar. He said every slide very.
Hello. ये क्वेश्चन अपने पास रहेंगे. या मिस्टर भाई के मवाले सर ये उनका लग रहे हैं कि you asked about in Vallabh Nagar the carbonated area, how it formed, any source of mineralization. Well, I am not the man of economic geology, I am the man of structural geology. So from the source of mineralization from depth, I can't discuss because I am a structural geologist. Yes, Murli, you did ask about the question aspect of mineralization in zone pegmatite, granitic pegmatite, please. So in zone pegmatite, I mean, we are not getting any sort of metallic mineralization. We are getting some mineralized zone, and from where the people are mining some gemstones and mica and other thing. So zoning and other thing are not structurally controlled. The structure of pegmatite has been explained by many workers, different type of pegmatites we are getting. So we can go through that and you can have idea about the aspect of mineralization in zone granitic pegmatite. Thank you.
Yes, sir. It was connection error from my side. I come back.
Okay. There is, I'm going to answer one question from Ronak Jain. Mineral concentration is more at the closure of the fold or hinge. Now listen, hinge is rather to say a linear feature and fold is a three-dimensional feature. So the hinge zone where we are getting maximum mineralization, as I've shown you in case of structural folding, this is loci of the least pressure. Now, as I have shown you in the diagram, examples from the non-metallic minerals also, for the pyrophyllite also. I've also shown you the example from Java also. So most of the hinge zone, we are getting maximum concentration of mineral. In example from Pur, that is Tiranga area also. In ancient time, people were knowing that hinge is the region where we'll be getting maximum mineralization. Even other than what people might have not mined out there, the iron, but other than that also, very important minerals or noble minerals they might have taken out from the hinge region. Because of the mobility is more any mineral, it will go first to the hinge zone. So I think, Ronak, I'm clear to you.
Yes, it is perfectly explained. Meanwhile, I have one announcement, sir. We are shortly we are going to circulate the feed this attendance form. So please fill up the form and submit it. This is Google form. Over to you, sir.
I think this is we are now ending the Q&A session. So I would request Abhay to give a closing comment on this webinar. Abhay, please.
Yes, sir. There are so many questions are still coming towards to you, sir. I said we will, there is one last question from question.
Okay.
Sure.
So just a moment, sir. Just a moment, sir. How the organisms are formed?
Now listen, I mean, organised and other thing goes to the part of igneous subject. So I think it's not related to what structure or in structural geology we are doing over here.
Exactly, because it's mostly the structures are. So, sir, I have this another announcement for all the participants. We are going to send you this feedback form, and please fill up this feedback form and. So it was a very fantastic. Questions are still coming towards you, sir. But I'd like to announce that we will reply each and every question to everybody through email or WhatsApp through on their mobile as well. because its time limit is also there. So we have to close the meeting as well. Okay, this sorry, sir. Another question. In highly deformed area, low geopressure, I mean that area where the less overburden pressure at depth comparative to less deformation area. क्या बोला? This is question from Ankit. Sir, am I audible? So that was all about the presentation and question answer round. And on behalf of Geo Junction team, I'm Dr. Abhay Dashora, and it's my privilege to acknowledge a vote of thanks to Professor Chauhan. I thank all the team members for putting this webinar together. I would like to thank our speaker, Dr. Chauhan, for interesting talk on this webinar and for enlightening us with his commendable knowledge on the subject. Thank to all participants across the country and the world for their enthusiastic participation, contribution, and time. Special thanks to Mr. Santosh Lohar for always being solid behalf on Geo Junction team. It's my privilege to acknowledge a vote of thanks to him. I thank to all my team members, Mr. Shubham Daglia, Miss Diksha Pandey, Dr. Diksha Pandey, for putting this webinar together. I would like to thank our speaker, Dr. Chauhan, for interesting me such a webinar. And in future also, we hope you will guide us, and in upcoming webinar also, you will come and provide us more information. Thank you very much, sir. And last but not least, I would like to thank all the participants from India and various countries. There are participation from 11 different countries globally. So I'd like to thank you very much to all of them. You can ask a question, and you can follow us on Instagram, on Facebook, on YouTube as well, where you can ask anything to us. We are always we will always try to provide you more updates and information there. So keep following Geo Junction, and hope we will serve you better. Thank. Now I'm sending you attendance sheet. Attendance sheet link. So please fill up that, so that we can provide you certificate according to that. Yes. अरे यार, उसमें YouTube पे डाल. Yes, here is the attendance link. Show up in the yes, here is link I have posted on chat box. Please fill up that and so that we can issue the certificate to you. YouTube and yes, it is posted on YouTube as well. So please fill up, and it's time to it's time to finish our this webinar. Hope we all will together again and come with we will try to come with a new and interesting topic again very soon. So thank you very much for coming. Have a nice day. Thank you all geologists, geoscientists, and professionals. Thank you very much. Thank you.
So, Abhay, Dr. Abhay, Mr. Santosh, and the whole team, Mr.
Yes, sir.
and Mr. Arpit, Dr. Diksha Pandey, Mr. Shubham Daglia, and Mr. Chetan Chauhan for organizing this wonderful seminar. And I must thank Dr. Abhay. You had a nice idea by which we could meet, we could convey our very small thing which I want to explode and to apply to some mineralization. I'm sure in our life, with the help of this small scale structure, we are going to have a very big deposit in future. I hope, and I wish all you youngsters, all the researchers, all the geologists, please use this my hard labor which I put in the field and try to implement on the structural control of mineralization. So I once again thank you all, directly, indirectly, who are involved in this organizing seminar. Thank you once again, and see you in the next webinar. Thank you all. Have a good day.
Another announcement from my side to all the geologists and geoscientists. Anyone who are planning to visit Udaipur in the future can contact to us, and we can have some geological discussion or field trip together. So if anyone want to have field work with us or Professor Chauhan, who is always available for us, he is so kind. So can contact us in future. Thank you very much.
Thank you all. Thank you.
Okay.